In archaeology, determining chronology is essential to validate artifacts' historical significance. Dating methods include stratigraphy, which is relative dating, and radiocarbon and potassium-argon techniques, which are absolute dating. These methods contextualize finds within national and global timelines. For example, dating confirmed the Indus Valley Civilization's prominence and linked sites like Kalibangan and Lothal to the Harappan culture. Chronological validation lends credibility to a civilization's cultural, economic and intellectual achievements, transforming undated objects into historical evidence. Without dating, history risks being dismissed as speculation. Coins or seals occasionally provide clues, but stratigraphy and scientific methods remain vital for accurate chronology. Dual-method approaches ensure reliability, anchoring heritage claims in verifiable timelines. Dating methods are categorized into 1. Relative dating and 2. Absolute dating. Relative dating refers to determining the chronological order of objects through comparative analysis. This method allows archaeologists to place artifacts, sites, or civilizations into comparative historical periods, identifying them as older or newer relative to one another. It helps illuminate events like site construction, reconstruction, fire incidents, floods, wars, or other destructive events. However, it cannot calculate exact time periods or years. While estimates can be made, these are not always accurate. Despite its limitations, this method remains indispensable for uncovering intriguing aspects of the past, as no superior alternative currently exists. Different techniques are employed depending on the materials involved. Stratigraphy, developed by Neville Pitt Rivers, who lived from 1835 to 1902, and expanded in India by Mortimer Wheeler, analyzes soil layers. Layer thickness does not always correlate with time. Thinner layers may represent longer periods, for example, Paleolithic layers, compared to historical era deposits. Disruptions like pits or canals require careful analysis. Typology. This method dates artifacts based on shape, design and manufacturing techniques. Similar artifacts are assumed contemporaneous. For example, wheel-made pottery is dated later than handmade varieties. Typology also reveals cultural preferences and technical advancements. Flinders Petrie used this method to correlate Egyptian and Palestinian pottery, while Gordon Childe and Graham Clark applied it to European prehistory. Cross-dating, also known as associated finds. This technique dates artifacts using chronologically anchored objects like coins, inscriptions, or pottery. However, disruptions like erosion or mixed layers necessitate caution. Flinders Petrie pioneered this method in Egypt, while H.D. Sankalia used it to establish India's Paleolithic chronology. Geomorphology. This method studies landform changes to date prehistoric cultures. D. Terra and T.T. Patterson linked India's Sohan culture to the Second Glacial period, which was about 435,000 years ago. H.D. Sankalia dated early Paleolithic tools in India to 500,000 to 50,000 BCE. River terraces, lowest deposits and glacial-interglacial sequences help correlate human activity with geological events. Challenges include mixed layers, known as cross-bedding, and regional variations in sedimentation. Fossil analysis of Pleistocene fauna, such as elephants and rhinos, provides relative dates. Index fossils like Elephas pneumaticus from the mid-Pleistocene serve as chronological markers. Smaller animals like rodents are more reliable due to their abundance and limited migration. Plant fossils, such as lichen and moss, reflect climate shifts, aiding in correlating human settlements with environmental changes. Fluorine accumulates in buried bones over time. K.P. Oakley exposed the Piltdown Man hoax back in 1912 using this method. However, variability in fluorine uptake due to factors like temperature or bone type limits its precision. Paleontology, or pollen analysis, was developed by Leonard von Post in 1916. This method analyzes pollen grains preserved in lake beds or peat. Pollen sequences reflect vegetation changes, linking human activity to climate shifts. Sample preparation involves chemical treatment such as hydrochloric acid and hydrogen peroxide, and microscopic examination. Each method has limitations but remains critical for constructing relative chronologies in archaeology. Absolute dating determines specific calendar dates via natural decay or accumulation, for example, radiocarbon and VARV analysis. Independent of other methods, it's termed chronometric dating. Examples include materials decay rates to establish timelines crucial for precise historical and geological chronologies. They include the following. VARV analysis, developed by Gerard de Geer in the year 1878, dates geological events in solar years by counting annual sediment layers, or varves, formed in glaciated lakes. Meltwater deposits paired layers, heavy particles, which are coarse and spring-deposited with organic-rich dark layers, followed by lighter ones, which are summer-deposited calcium carbonate. Layer thickness, which can range from a few millimeters to 30 or 40 centimeters, reflects the climate. The layers are thicker in warm and dry periods and thinner in cold eras. De Geer's Scandinavian lake studies established a 15,000-year chronology, dating the Pleistocene's end to around 7,912 BCE, later recalibrated to 11,000 BP via radiocarbon. H. Goodwin proposed around 8,300 BCE. However, there are limitations. It's restricted to glaciated regions like the Baltic Sea and parts of South America. Ernest Antevs applied it in the United States, but the results remain disputed. Dendrochronology, developed by A.E. Douglas between 1901 and 1913, CE dates wooden artifacts by analyzing annual tree rings, which vary in thickness based on regional climate. Trees from the same era and area share ring patterns, enabling the dating of artifacts using both live and dead samples. Ideal samples contain 60 to 200 rings, as fewer than 25 to 30 rings are unreliable. Key applications include dating prehistoric Native American sites, such as those in the southwestern United States up to 3,000 years old. This method is crucial for regions lacking pre-15th century records. Limitations include the fact that dendrochronology determines tree-cutting dates, not artifact use, which risks errors if the wood was reused. Cross-validation with radiocarbon dating enhances accuracy. Potassium-argon dating, developed by C.F.B. Weizsäcker in the 1920s and applied by W. Gentner in 1950, this radiometric method dates volcanic rocks via the decay of potassium-40 into argon, which is about 12%, and calcium, which is around 88%. Ideal samples such as lava and obsidian trap argon upon solidification, enabling dating from 30,000 to 300 million years. Key applications include the layers at Olduvai Gorge, which range from 1.9 to 1.5 million years, and Lake Turkana, which dates to around 2.6 million BCE. Limitations. Argon loss during analysis and uneven potassium distribution cause about 10% error margins. Potassium-40, which makes up 0.011% of potassium isotopes, requires precise measurement of potassium-39, potassium-40, and potassium-41 ratios. Thermoluminescence dating. This method dates heated objects like pottery and bricks by measuring trapped electrons released as light upon reheating. Radioactive elements such as potassium and uranium, along with cosmic rays, ionize minerals, creating electron traps. The light intensity corresponds to the time elapsed since last heating, ranging from 400 to 500 degrees Celsius up to 1200 degrees Celsius. This technique was pioneered by Farrington Daniels in 1953 and later applied to archaeology by G.C. Kennedy in 1960. It helps authenticate artifacts by calculating the equivalent radiation dose absorbed annually. Limitations, soil contamination and cosmic ray variations introduce errors marked by plus-minus symbols. Radiocarbon or C14 dating. Developed by Willard Libby in 1949, this method dates organic materials by measuring C14 decay, which has a half-life of 5,730 plus or minus 40 years. Living organisms absorb C14 via photosynthesis or diet. After death, decay begins. Measurement involves analyzing the carbon-14 to carbon-12 ratio using Geiger counters or accelerator mass spectrometry, also known as AMS, extending the limit to about 70,000 years. Key applications include dating charcoal, bones and shells, as well as validating timelines for artifacts, such as Egyptian artifacts. Challenges include atmospheric carbon-14 fluctuations from nuclear tests or fossil fuels, contamination risks that require meticulous calibration, and the old wood problem where reused materials can skew dates. Calibration involves cross-referencing radiocarbon dates with dendrochronology to correct discrepancies, for example, Libby's 5% error for dates before 2000 BCE. Modern labs, like the Tata Institute in Mumbai and the Groningen lab in the Netherlands, employ accelerator mass spectrometry, or AMS, for greater precision. Chronology anchors archaeology, distinguishing historical fact from speculation. Relative dating, such as stratigraphy and typology, sequences artifacts, while absolute methods like radiocarbon and potassium-argon dating assign calendar dates. Cross-validation, for example, dendrochronology calibrating carbon-14, resolves discrepancies, enhancing accuracy. These techniques validate milestones like the Indus Valley Civilization and Olduvai Gorge's early hominids, contextualizing cultural and technological evolution. Challenges such as argon loss and carbon-14 fluctuations demand meticulous calibration. By merging stratigraphic layers with isotopic decay, archaeology transforms relics into evidence, bridging past and present. Precision ensures undated objects become milestones of human progress, preserving heritage and fostering global historical narrative.